VDS, right? VGS and VDS, and it will be depending on how NMOS is going into the saturation, how it is going into the linear, how it is going into the cutoff. So, and please do not make up your mind that one device means initially it is cut off, then it will go into the linear active or linear region, then it will saturate. No, it is not like that. So depending on the voltage, depending on the terminal voltages, then it will be, I mean, after cutoff, one transistor can go into the saturation. After saturation, one can go into the cutoff, one can go into the linear. So it will be depending on the, so device, this is another part, another, so I should not enter. So roughly, I mean, to make it easy, so roughly we are estimating that in case of NMOS, if one I mean gate is given, I mean get terminal gets 1, then it will be on. Or PMOS, if it is getting 0, it will be on. To make little deviations, I hope all of you are familiar with the digital circuits. I mean, gates, everything, all of you are familiar. So I need some responses. So you please respond. So then I can proceed. So how many, any one, I mean, very childish questions, please do not mind, but please try to answer so that I can ask you again. So how many gates are there? Anyone, please, if you please respond. Anyone, please. Am I audible or not?
7 gates are there in digital circuits.
How many?
7 gates.
How many gates are there? 7.
7, yes, sir.
Okay. May I know your, I mean, I am in presentation mode. I cannot see anyone right now. I mean, who, may I know your good name, please, sir?
My name is Gurminder.
Okay, sir, why 7 gates are there? Why only 7 gates are there? Why not 9? I mean, why not 11? Why only 7 gates are there? Anyone?
Sir, gates can fulfill the requirement, subtraction, multiplication, all these arithmetic operations.
No, can you, I mean, if we try, can we introduce one more gate?
Yeah, sure, sir. It will depend upon the requirement.
Have you heard about, I mean, except these 7 gates, have you heard any other gates?
No, sir.
No. Okay, anyone else? Why only 7 gates? I mean, that you see, I mean, the answer, please do not take it, I mean, different. Yeah? The answer you have given, I mean, why 7 gates are there, that is looking like a consolation, I mean, self-consolation. That is not the justified answer. Anyone, please? And why 7 gates are there? Why not 9? Why not 5? Why not 3? Why not 11? Why not n numbers? What could be the reason? Something? Any idea? Anyone else, sir, madam, please? Okay. Let me just tell you. So, what are the gates? I mean, it is looking like okay, AND gates. I mean, some figure is there. Oh, I'll be drawing this, then aisa round karega. This is one AND gate. What is NAND gate? Oh, it is looking like AND gate, and then in the front side one bubble is there. So these are for us. These are for this symbol. So we are very primitive human being. These are symbols. These are for the human beings. Circuit will not understand. I mean, what kind of circuit will only some connections, right? How signals. So in Boolean function, we have done so many optimizations, right? We have done so many optimizations. Whatever may be the Boolean functions, the most optimized 7 Boolean functions are termed with the names of the gates. These are the most optimized 7 Boolean functions. And one XOR, let's say if I am giving the when the students are coming newly introduced, newly gates, then if I am giving a bar b plus a b bar, then he might be thinking, I mean, as he has learned, I mean, Carnot map, he might be thinking that yes, I can optimize it, sir, I'll put it, but finally you will see that cannot be optimized. So gates are most optimized 7 Boolean functions. Gates are most optimized Boolean functions, and those are represented, and then we have made some symbols that is for our human being for learning purpose. But gates are 7 optimized Boolean functions. And if I am giving you some equations now, you are familiar with y equals to ab, you are very familiar, y equals to a plus b, very familiar, y equals to a plus b whole complement, very familiar, this is NOR gate, y equals to a bar b, very familiar, I mean a bar b plus a b bar, very familiar, XOR gate. But if I am telling you that a bar b bar c plus a b bar c bar plus a bar b c bar plus a b c, can you tell me either that could be optimized or not? You'll be asking, sir, I need to write this. How? I mean, verbally you are telling how. Yes, but this is very important. Whatever I have said, that is the sum equation. That is the sum equation. Sum. Right? I know that most of you know the full adder, right? So full adder, sum and carry. Those 4 main terms are there in each sum and carry. Now here you see, anyone, can you tell me if you are having, I mean, copy and pen, please write down some equations. So a bar 4 min terms, so a bar b bar c plus a b bar c bar plus a bar b c bar plus a b c. These 4 min terms, either that could be optimized or not. Anyone? Yes or no? At least guess, yes or no?
No, sir, they are already they are in their canonical forms.
Okay. So they cannot be optimized. Right, sir? So optimization, sir, I just want to know, I mean, canonical or non-canonical forms, that does not means either it is optimized or not optimized. Standard canonical form is there, and in digital, if anyone is interested, if you go through D. Roy Choudhury, Platinum Publishers, most probably part 1, part 2 is there. That is dictionary, digital dictionary. I mean, if you please, I mean, most of you I know, I mean, that one popular book is there, Mano is there, but that is very, but I mean, beyond that class, beyond that, if you would like to go, that is a tremendous one. You'll get the full view. So anyway, so that is not because of canonical form. Now, okay, let me make it very easy. Y equals to AB. Just now, I have given you one idea that most optimized Boolean functions are represented by gates. Fine. So y equals to AB, one AND gate. Now, y equals to A dot B dot C means 2 AND gates, or one can say 3 input AND gates. Okay, if not 3 inputs, if two input AND gates means 2 AND gates are required. So can we optimize y equals to A dot B dot C? Can we optimize? Not required, right? We cannot optimize, na? Am I correct? Okay, so y equals to a dot b dot c dot d dot e dot up to dot 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 n. Can you optimize this? This cannot be optimized. Similarly, y equals to a XOR b, it cannot be optimized. Again, y equals to a XOR b XOR c, it cannot be optimized. Y equals to a XOR b XOR c XOR d XOR e XOR f XOR up to XOR. So if any function represented by similar kind of gate, that is in ANDed form, I mean maybe AND or that cannot be optimized. Like y equals to a dot b dot c dot e dot means so many AND gates are there, that cannot be optimized. But if any equation is written and or not or and or whatever in any combinations, that can be optimized. So that is the reason why the sum equation, or maybe you have done that what is that popular circuit, odd that for sending odd numbers and odd number, even numbers, odd parity checker. Similarly, you cannot optimize parity generation and checker, because all these are for, I mean, XOR or XNOR format. So these are the things. These are the things we need to analyze it properly in digital also. So how those are coming and what are coming, how we can represent it. And can you give me one example where we used to use XOR gate in our daily life, in your home? If you are having first floor, I mean 2 floors are there in your building, and if you would like to go from first floor in the night time from ground floor to first floor, then you have to light on the light which are on the stairs, right? So in below you have to have one switch, so double way switch, and in top also you have to have another switch, and those switch are connected in the XOR format. So one has to be on, another has to be 0, then only light will be on. So these kind of I mean gate operations we are utilizing, we are using it in our daily life. So anyway, and okay, so and another interesting, let's say if I am asking all of you have anyone? Okay, so another interesting point, let's say if I am asking you to design one NOT gate using NAND gate. So anyone please give me answer. So design one NOT gate using NAND gate. So how can you design?
Short the inputs.
Short. Okay.
Yeah.
So who told this one?
Dr. Mognonil Goswami sir. My name.
Goswami sir. Okay, Goswami sir. So others, anyone else? If any different answer or same answer, anyone else? Any idea? Please. And all of you will agree with Goswami sir. Okay. So Goswami sir, are you in NIT Manipur, sir?
Sir, I am from Chandigarh University.
Chandigarh University, sir. I mean, I hope all of you are matured. Please take it. I mean, the next thing I'm going to tell you, please take it lightly. I mean, for the analogy purpose, do not take it any other way. Let's say I am young. Okay, let me, I mean, put forward towards me. Let's say I am young. Okay, now I am doing my, let's say, master's or PhD, and during my period, I'm having, let's say, then maybe I'm young and मैं तो ऐसा हो गया, क्या करूँगा, ठीक है, चलो दो girlfriends है. Now after my PhD, now my family, they are pressurizing. Now you have to be you should get married, you have to be settled, this and that, because now you'll be getting job. So if this is happening, then what would be my solution? Should I tie up both my girlfriends to make it one? Is that possible? Practical. This is not the practical solution. So I'm a little clever one, let's say. I'm very tricky. I'm a bad person. So what I will be doing, I mean, using internet, I'll be finding one job for one of my girlfriends in the USA. Then I will say, no, she will get the job and she'll go she'll go to the USA. And now in India, I'm a little relaxed. So only one girlfriend is there, I can get. So there won't be any problem. And this is, I mean, in a light mode, this is also a good, a practical solution. One of the solutions. This may not be good. This may be one solution. So why you are tying it up, both the legs? Why you are tying it up? Because if you are tying it up, whenever you are tying, then what happens? One may be shorter, one may be longer. Means mismatch will be there, that may be there. So instead of this, if one leg is connected to USA means 1, and another leg is connected to your input A, so A dot 1, then automatically it will be complemented. So why? I do not know why. I mean, because in one book it was shown. I mean, both the inputs are tied up together. But whenever we are concentrating on low power, whenever we are thinking in a different way for different reasons, this could be better solution. I mean, some of you have heard, I hope, static power, dynamic power, so many things. So
I have an objection, sir. I have an objection with connecting that to logic high, because whenever we are giving logic high, that means it is constantly consuming voltage. The drop would be there, so the voltage consumption would be higher.
Dynamic power. You are talking about dynamic power. Yes,
exactly.
That is exactly. Yes. Correct. So different. Yes, and okay. The way you have said, sometime, let's say, whenever, let's say one is firing, and whenever one is firing, I mean that क्या बोलता है वो जो, anyway, firing means that bada wala gola. Okay, whenever firing, angle has to be perfect, right? Angle has to be perfect. Otherwise, bombing. Otherwise, bombing may be happening, maybe on locality, maybe on school. So with that 0.001 deviation with that angle, that may dislocate your target. That may target in a different way. So sometimes what we need to do, we need to be very precise. I mean, in terms of security, we need to be very precise. Instead of, I mean, in some cases, instead of thinking of bothering of dynamic power. So if mismatch, that's why I told, if mismatch is there, then in the output, whenever we are desiring logic 1, then due to mismatch for very few picosecond, the output may be wrong. So because of that wrong output of one gate or one segment or one system, the whole system may misbehave during that small period of time. And because of that, there may be some security problem. So sometimes, instead of doing that, instead of tying them together, if dynamic power, yes, I mean that you have not turned, but that is called the dynamic power. Dynamic power will be high. Correctly, you have mentioned correctly. That is correct. But if we are looking for static, that static power will be low, and also the error, I mean that chances will be low. So anyway, options are there. So tying up, yes, logically this is correct. Whatever Goswami sir told, that is correct. Logically, this is correct. So this could be done for NAND gate, and for NOR gate, I mean that legs that could be connected to 0. So whenever we are connecting it to 0, then the dynamic power that you are talking about, then it not be there. I mean, it will not be there in case of whenever we are tying it to US. But if we are tying it to another, I mean, 0 level, ground level, there may not be. And then the leakage will be reduced. So many pros and cons are there. So what is the problem in VLSI? What, sir, please. Okay. Okay. So where is the challenge? Not the problem. Where is the challenge? The challenge is how to optimize, because in circuit, if you are decreasing power, then delay will increase. If you are decreasing delay, power will increase. So we have to go for best of both worlds. So that is not an easy task. So anyway, so these are the there. So I would I'd like to give you some one way of thought process. This is not the only one, but this is one way. So SRAM, so read operations already I have spoken about. Similarly, SRAM write operations. Anyone trying to say something? No. I hope I can continue. So read write operations, whatever I have discussed just before. SRAM sizing. So this 6 transistor SRAM is having one major issue. Leakage is very high. What happens? Two inverters are there. I mean, in a very generic way, if you are considering left side is one inverter, right side is one inverter. No, apart from this one, you see, right side upper one PMOS, right side upper PMOS, and left side lower NMOS. These two are also forming one inverter. Similarly, left side PMOS, right side down NMOS. These are also making another inverter. So how we can control their linear part and saturation part? That is an issue, and because of that, and I hope you do remember, I mean, voltage transfer characteristics. In the voltage transfer characteristics in the left side, I hope you do remember, left side that is the high, right side that is the low, and between left side and right side, one region is there where it is coming down from high to low. That part, that is called the, I mean, if I'm asking you inverter, what is this? Is it digital or analog? 99% this is digital. Not exactly. I mean, whenever we are dealing only that logic 1 or logic 0 part, that is the logic wise, at least that is the digitized one. But analog is also there in the middle, and analog is also there. And whenever we are discussing digital, we cannot discard analog, I mean, directly. So in middle part, where each and every point is having different value, then normally we used to consider these are the analogs. So these analog part plays important role, and during this time, actually snake path, I mean, huge current flows, and during that time, both the NMOS and PMOS both are on, which is not quite often in case of static CMOS. So why we used to consider static CMOS? Why this is very popular? Normally we used to consider whenever PMOSs are on, then NMOSs are not on. Whenever NMOS is on, then PMOSs are not on. Vice versa, at least input wise. But for certain period of time, very small period of time, both NMOS and PMOSs are on. That will be creating problem. So SRAM sizing. So design wise, this is okay. So what would be the exact size? So normally the PMOS, those are connected to VDD. Those will be, I mean, little, I mean, here, I mean, for this transferring logic, little weak, and NMOS is supposed to be little strong. And then in the NMOSs, left side and right side, those two NMOSs means which are connected to word lines, those are size to be, I mean, medium. Here I have written strong, medium, weak, or low. These are, I mean, I have not given any specific value because that will be changed in terms of your technology, in terms of, I mean, which technology you are using. And if we are doing, I mean, digital logic, normally we used to keep constant the L supposed to be, because normally for MOSes we used to let's say 65 nanometer. What does it mean? The channel length means length of MOS is 65 nanometer, and width supposed to be, and here in MOS width are more than the length. So with a minimum, it is supposed to minimum, it is to be 2 times of L minimum. And in case of PMOS, it is again another 2.5 times of in MOS. Normally we used to take 2 to 3 times. So widths are more. So if you are changing, I mean weak, strong, or means we in terms of sizes. Sizes means, to be very specific, in terms of more width. And bit line conditions, here you see. So as we discussed now, bit lines. Bit lines, what is that bit lines? Conditioning. Why conditioning? Because bit line little difference, little 0.001 difference will create a problem. So that's why conditioning. So that kind of conditioning is required. So here two circuits are shown. Here you see we are using phi in the middle, phi complement phi is the one there using PMOS. That's why phi we are using. And here you see if we are using, so both the PMOSes will be on bit and bit line. Both will be getting. So in case of read, both will be getting the same value, similar kind of value, but still we do not know. So during the fabrication, the left side PMOS may little differ from the right side and vice versa. So if that is there, again there could be a problem. Again, to optimize that one, again in the middle, the lower figure, again we have introduced another PMOS. So how to make bit and bit line exactly? In words, though I have said you just apply VDD by 2. But how to apply VDD by 2? How you will be getting VDD by 2? If I am asking you, I mean in our home 240 volt is there. I mean if I am asking 220 volt is there. If I am asking no, you take 110 volt. How easily you will be getting? So it is not that even if you are very efficient electronics engineer, if you are making one circuit and that may not give exactly 110 volt, that may give 110.1 volt. So these, because now we are in fine-tuned mode, so these difference matters. So that's why I mean giving you some idea. I mean how that is to be minimized as much as possible. So these are the some bit conditions. So SRAM cell operating principle. Okay, I am skipping this one. Okay. Now let us start. What is CAM? What is CAM? Right. So CAM, what is CAM? CAM content addressable memory. What is that CAM content addressable memory? Content addressable memory. So in memory, just now we have discussed that some data could be write, some data could be, I mean after some time that is to be read. I mean we are keeping data means we will be utilizing data. Now CAM what it does, instead of direct, normally we search with, if I'm asking my mother, so where is the, she used, where the haldi is kept, she used to answer, it is in the right side upper rack. Means she used to tell me the location, right? She used to tell me the location, but how that location would be generated. So whenever we are searching data, we do not know the locations. We want to know the location, because my memory would like to play my mother's role. Who will be the mother? So that mother, that is the CAM, that is the content addressable memory. So in the library, catalog is the CAM. So in the bank, I mean your account number, that is the CAM. So when CAM, what is that CAM? If we are putting data, content, let's say, I mean the way we are making Google search, we are making some search content, we are writing something, we are writing some keywords. So with that keywords, if it is matching something, then it will be giving in the first page, second page, and so on. So similar things in hardware. Now you'll be sir, in the software it is there. Why it is required in hardware? For our purpose, it is software, it is okay, but for the machine purpose, for the security purpose, hardware is more convenient, and also for hardware is required. In some cases you cannot utilize, you cannot make all the software, But nowadays we have made some combinations of hardware and software. I mean, this kind of, I mean, let's say network routing. For the network routing, we need to route it, I mean, through that device. So this is where the need of CAM. So content addressable memory. So in memory, one memory is there. If we are giving some content, and then it will compare with this content, and when it is compared, then it will, it is comparing means, let's say what I am trying to say, let's say I am looking for a solid state device book. Means I am not looking for solid state device book. I am looking for the book for reading the content inside it. Let's say, any let's say energy band. I would like to read energy band diagram of diode or transistor. So for that reason, I am looking for solid state device. So if I am giving solid state device, then it will point out one location. So in CAM, we are giving solid state device, or we are giving Streetman Banerjee, or author's name. Then it will compare. Either if it is comparing, when as per the comparison result, it will give some data. So that's why in the right side you see. So we are comparing data 0, 1, comparing data. Then it is producing one address. It is producing one address in the down figure also. We are comparing data 0, 1, 1, 0, 1. Then it is matching with something, and then it is producing one address 0, 1. So this is the very basics. I mean, how one content addressable memory works. So these are content addressable memory, very basics. I mean, normally we used to use it. In case of ATM card, we are using. In case of network also, very few part. And in case of cache memory, we are using. Sometimes whenever you are giving something writing, and automatically it is coming into your browser, everything. So in cache memory, we are using that is fabricated inside. Cache memory within the processor, it is fabricated so that immediately, very specific selected data. In computer, I am not in computer science. So in some of my colleagues, they are working. What would be the cache memory, and what would be the priority which would be kept in the cache memory. So cache memory contains actually CAM, content addressable memory. SRAM and CAM. So RAM versus CAM. So what is that? RAM versus CAM. Let's see. In case of RAM, so data are there, we have to give the address. And then we will be getting the data. This data is selected, and we will be getting the data out. In case of CAM, we are getting, some data. We are providing data input as input, and it is matching with the data, and as per matching, it is generating address output. Now you think, you please imagine the right side figure, you bring it in the left side, and left side figure, you bring it in the right side. Then it will complete your memory structure. So we need address out. This address out will be address in for the RAM, and from the RAM, then we will be getting the original data. So all these are in forms of 1, 0 because it is binary. But the data out here, that is different, and data in here, that is different. So that is data. Let's say I'm writing ANUP, ANUP. So that is the data in. And accordingly, ONUP related all the account information, it is generating right side. It is generating the address out. This address out is going into left side, that's column number 4. And then it is giving 10110001. So this is giving data out. This data is actually my account information related all the data. Here for the sake of, for less space, I am showing some bits only, but this one left side is huge data. So this is the difference between RAM and CAM. So CAM for routing table. So using CAM, we can use it. Which port that to be selected, which port not to be selected, which what would be the, so search based on the search data, and then search result, some address supposed to be there, and then accordingly the output would be, the port would be selected. So for routing, so what I'm trying to say, one is CAM. Similarly, we are giving the analogy. We are giving the analogy inside such a way so that you would be able to understand where specific applications are there for CAM. And already, believe me, already we are using CAM type of memory. We are using in all our cards, in all our some memory, bank account, everywhere we are using, and in routing also. And we need to develop something more, and that is what I'm trying to tell. So normally we consider, that is we consider means two types are there. So binary CAM, and most of the people they are working on binary CAM. So BCAM and TCAM, ternary CAMs are there. BCAM and BCAM, and BCAM means 0 and 1s. Ternary CAMs, we have introduced another conditions, because in binary, so 0, 1 as well as don't care conditions are there. So don't care means, either it could be 0 or it could be 1. So don't care conditions here. So now slowly I'm entering into the research mode, into the research problem. So I'll be discussing you with some research problems. So that will be going through. So don't care conditions, that could be nicely handled, that could be nicely utilized, and that is highly required. So that is for ternary CAM. So ternary means three. Binary means 2 bits 0 and 1. Ternary means 3 bits 0, 1, and don't care. Don't care means it could be 0 or 1. It could be anything. Acha. Then we'll be starting need of masking, means don't care conditions, how efficiently it could be analyzed. So I will take just 2-3 minute break, and in the meantime, if you have any questions, you can frame it out, and I'll be taking exactly 2 minutes break. Okay. So Kullan, so can I take 2 minutes break? Kullan sir. So others, am I audible?
Sir.
Sir.
Yes, sir.
Okay. I'm taking just 2 minutes break, please. Huh? Let us resume. So just now, we have discussed binary and ternary. Ternary means third bit, and third bit is little ambiguous. 0 or 1, 0, 1, whatever it may be. So this is the spirit, whatever it may be. So with this concept, with this spirit, then we can do the masking. What is that masking? Masking means thoda dhakkan, right? Masking means dhakkan, or in other words, if it is wide open, then also it is masking, right? So if it is wide open, whatever it may be, then also it is masking, right? So what is that masking? How we can do masking? Yes.
அப்ப அதுக்கு வந்து நான் சும்மா அப்படி கொஞ்சம் நிறைய ரெஃபர் பண்ணி கொஞ்சம் எழுதி வச்சிருக்கிறேன்.
Are you asking me some questions or anyone is talking outside? Okay. May I continue? Kullan sir, Goswami sir, others, may I continue, sir?
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
Okay.
So what is that masking? Masking that could be done. Masking means, let's say 5 bits are there. 5, let's say my name is Onup Dandapat, right? Let's say you search for Onup, then you need to mask Dandapat. So if it is matching with Onup, I would like to see Onup. So it will give me Onup. Onup related data. So whatever the matching, mismatching for the Dondo part, I mean my surname, so it don't matter. So this kind of masking we can do. So masking that could be done in a 2 different way. One is local masking, another is global masking. What is, I mean, we are putting this terminology. So what I am trying to tell, I am putting you some research problem. So local masking and global masking. What is that local masking? Local masking, let's say, I mean, all of you have seen hostels, so many hostels are there. Let's say hostel IP range, the first one you see 10.10.1.55 to up to 86. Let's say total 55 to 86. So let's say total 30 or 31 students are there. Right. So in this hostel, now if I would like to, let's say from our internet center, they would like to control who is doing something wrong, right? Or something is there. So what we need to do, we need to search for that specific persons, and for searching specific persons, we need to search between 55 to 86. No need to search 10.10.1. So if there is no need to search for 10.10.1, then we can mask those things. I mean, those, if we are masking, then we would be able to consume, we would be able to consume less power. So searching for 10.10.1 is not required for any specific hostel. This kind of specific applications are there. In this kind of network or routing applications, we can utilize this masking. So with this concept, I hope now you would be able to see. Now first you see global masking. What is that global masking? So data are there in the CAM itself. Data are there. In the data, if when in the search key, in the search data, if one bit or 2 bits or whatever you wish, so that is masked. Masked means cross. We are writing here cross, but we have to design the circuit in such a way so that either it is matching with 0 or it will be matching with 1. Cross for our understanding, but bit 1, bit 0, that will understand by the computer message. So cross means either it is 0 or it is 1, that will give the match. So it will be matching here, it will be matching 2 rows, 64 and 68. 2 rows will be matched, right? So we are masking one bit. So whenever we are masking one bit in the search key, then we are giving terminology that is the global masking. And when then it will giving match, and accordingly it will generate two addresses. And if you are asking me, sir, why two addresses, how to process, that is different part. Again, priority encoder, priority, those will be there. That is different. But this is the global masking. You please concentrate on the masking part. Again, local masking. What is the local masking? For the local masking, the search key will remain intact. Means search key, they will not do anything. But whenever we are asking, let's say in 64, in the 64 row, we have put one cross. So that is the local masking. So in the stored data, if we are masking, then it is called the local masking. So when we are making global masking, then we have to put the masking in the search key. And if we are making local masking, then we have to put in the stored data, in the stored memory data. And here also we are getting two locations. So local match. So this is the first one is local match. And lower one I have written, you see, match, only match. And in the global masking, both I have written. So all the terminologies, all the write up, that is with the very specific one. Okay. So this is binary cam versus ternary cam. So now I hope you do understand what is the difference. So this is nothing but the upper one is binary and the lower one is that is the ternary. Ternary means we are putting the left global or local masking. That is this is the basic cam cell. You see the left figure, that is the basic cam cell. In this basic cam cell, the upper one is SRAM memory. You see the bit line, that 60 SRAM we have written it. And the lower one, then and the middle one, that is the comparison circuit. Two NMOSes are there and two NMOSes are cross connected. You can make different connections, cross connected. And finally one evaluation logic is there, and that is the very basics, very conventional one. This is shown up over here. You can do ample modifications, and that is possible because this is a new topic, new area. So comparison circuit, yes. Okay, so and in the 60 SRAM cell, bit line and bit line bars are there, and on top word WL means word line. And here in the comparison circuit, you see search line, SL and S line. Search lines means search line and search line bars are there. Means whenever we are searching for any data. Anyone say it? Okay. Anyone searching for any data, for that purpose, search line and search line. The way we define 1001, we are looking for search data. So this is the one cell for one bit. So search line and search line bars are there, and accordingly that lower NMOS that will generate something, this ML match line. So these are very important terminologies. So bit lines, search lines, word lines, and match line. ML means match lines. So this match line, so this is the ultimate one, and for one cell this is 1 ml. So many cells, those are to be connected, because one word means it contains maybe minimum 8 or 16 bits are there. So means 16 cells will be there. 16 bits in one word, 16 bits are there, means 16 cells will be there. So how those 16 cells, those would be connected. So this is the ML, right? Match line. And finally in the right side, so I have shown, you see so many cam cells are there in the array, cam cells are there. And in the right side, you see I have written, I have drawn some PMOSes are there, and PRE means precharge. PRE means precharge. So every time the outline, and here you see all the cams ML are connected together. All the cams, all the MLs are connected together. MLs are connected together how those are connected in series or in parallel, how those are connected means it is coming through the circuit, right? So depending on the connections of ML, so two different CAMs are there, two different MLs are there, NAND type ML, NOR type ML. What is the NAND type ML? You see in this architecture, the first architecture, it is ground. I hope you understand this one. Here you see left side is grounded. Then ML is coming in the right side, bottom, right? ML is ground. So here you see that ML, that in the next second cell, it is going into the second cell that will be connected here again, means series connected, and so on. That finally we will be getting ML1, and for next row ML2, for next row next ML M-1. So these kind of connections, if these are series connected, like pull down network, if these are series connected, then those are called the NAND ML, means NAND, and I mean those are made almost analog. ML sometimes sometimes are called NAND type CAM, means NAND type MLs are connected. And what is that NOR type? NOR type, you see, those are connected parallel, those are not going into the cell. And MLs are connected parallelly. Parallelly means it is not as simple as it is shown in these blocks. Those are connected through some MOSes. Those are connected through some MOSes. Some control circuitries are there. So accordingly, those are connected. It is not like that. I mean, those are the way it is shown. It will be, otherwise it will be where and so it is not like that one. So if this kind of structure is there, then it is called NOR type ML, or NOR CAM. So based on ML structure, match line, match line. Now you can ask me, let me go back to the CAM architecture. Sir, if such data match with the stored data, then ML will be high or low. It will be high or low. It will be depending on your connections. Normally, I mean, ML is high means match. That is true for NOR ML. ML is low. That is true for, I mean, if matching, then also it is low. That is in case of NAND. Normally, but it will be depending on your connections. And again, this is another way of showing architecture. We have made these designs. So TCAM array, we have made the block 1, block 2, block 3, block 4, and each block is having its own circuitry, and all these are replicated again, and we have fabricated this one, and we have made it in such a way. And here you see some encoders are there, some multiplexers are there. So encoders and multiplexer, actually they are talking, they are introducing one block with the another block. So which block to be activated when? So these decisions, for these decisions only, I mean, some associated circuits are required. So these are the 4 planes for area optimization. So for area optimization, for power optimization, and for easy handling of A also. And also, if we are making, let's say, if for memory, if we are making too long, then memory itself will be taking a huge power. Then instead of reducing power, then we will be giving more power. Like our what is called carry look ahead adder circuit, right? So carry look ahead circuit, carry one circuit we design so that we can see the carry ahead, look ahead. We can see the carry ahead before the computation. But if we are making for 8 bits, then the carry look ahead circuit itself will take more delay and more power than the ripple carry adder. So we have to go for optimization everywhere. Okay, so these are the macros actually. Okay, so now I will be giving some research problems. So research problems means some idea whatever we have done, you can think of. And so if our motive is to generate address, I mean using cam to generate address, then we are thinking that instead of m cross n, only we can take two rows of cam. The upper cam, you see, all are given 1, and the lower cam all are given 0. So if we are looking for any search data, let's say 1011, then what is to be done? Then it could be done like this: 10 means upper one matching, lower one mismatch, then this, then this, then this, then automatically it will be generating a 1. So if our only motive is to generate specific address, then we can utilize cam in this way, so that only 2 rows. So here again we are thinking for specific applications, we instead of designing m cross n cam, m cross n means it will be huge. So instead of that, if we are using, I mean 2 into m plus 1, only this much of cams are required, and in this way we can generate the address. So this is dual bit. We named dual bit structure and ML control. So total associated circuit is very, very complicated, so that cannot be explained. So here you see the upper one and lower cam is required, then a mask storage in the left side. Mask storage is there, means for ternary, so masking also we are doing. In the right side you see upper comparison circuit, and in the lower side lower comparison circuit. So which one? So comparison is required. So it is block wise it is very easy to understand, but again it needs huge attention to complete the circuit. So here 2n plus m number of cells, instead of m cross n. So this is the advantage. So here only our focus is, if we would like to generate specific address, then that generation with the data that could be done using 2 rows. Research problem 2, segmented ML. So ML, we are doing something, every cell. In the every cell we are checking either it is matching, mismatch. In middle, if any mismatch is there, then ultimately total line will be mismatched, right? ANUP, if n is not matching, then then total mismatch will be there, means total name Anup will not be matching. So this kind of matching, if this matching is done separately, so what and we are talking about 4 bits, but if it is 128 bit longs, then what we can do parallel something. Here is, you see, in the middle one control circuit is there. ML, that is one control circuit, that is ML control circuit, right? This one, precharge and control, ML precharge and control. So this ML precharge and control, we can put it somewhere. So in the left side it will be checking something, in the right side cells it will be checking matching or mismatching. And so if we can do it parallelly, and then from both the sides if the data are coming into the middle side, ML precharge and control circuit, and then it will be taking decisions. So we can reduce time, at least we can make it half. Now the question is where we can put the ML. Let's say 128 bit long. If 128 bit long, then should we put it after 2 bits, should we put it after 4 bits, or should we put it in the middle? So which one would be convenient? So we need to make some research, we need to make some search for that purpose, right? So it is okay. So we have to do some research. So segmented ML. So how we can segment the ML? So for the convenient. Then again match line segmentation. Here you see I have given one one just to have a view that I have given it. I have put one ML control unit, and in the left side match line section 1, in the right side match line section 2, and some associated, and we have not shown the complete CAM structure, only the control ML part we are showing it here. So ML part that is here, and from the left side if it is matching, and the circuit is done in such a way, in the left side if it is mismatched, automatically it will deactivate the right side, and so on, and vice versa also. So where we are keeping the control circuit, that matters a lot, where we are keeping the control circuit. Either, I mean, normally we have shown, if we are keeping after 4 bits to 8 bit, in case of 128 bit long, then power optimization, again delay. So PDP and EDP, those differs actually. So very difficult to conclude, but we have seen from 4 bit to 8 bit, it is giving the, I mean, best of both actually. Okay. Another research problem, problem, precharge free CAM. So what happens in CAM? ML means match line, every time before search operation we have to precharge. In conventional, every time we have to precharge, means one match line 1, that has to be precharged to 1, and then as per the logic, either it remains 1 or it will be 0. So every time we have to precharge. Means like some time is required to precharge. So in the upper timing diagram, here you see. So first we have write operation. So we have to, for memory, we have to do the write operation. Then we have to precharge it. Then the ML line has to be precharged. And after precharge, then we can make one search operation. Then again we have to do precharge. Then again we have to do search operations. So precharge, search. But now we are approaching, we are proposing one kind of circuit. Can we do this kind of circuit that after write operations, precharge is not required? So if precharge is not required means we have to make the circuit in such a way so it will be self-precharged, means logic-wise output will be 1 or 0 as per the matching or mismatching. So no external precharge is required. Or in other way, we can say that we will be making the circuit in such a way so that it will be self-precharged. So that is also possible. So that way, if we are reduced, the precharge section is not there, then you see within half cycle we can do in the upper section up to the half cycle we can do one search, and here in the lower section after write we can do 2 searches. So 50% reduction in time. So 50, it's a huge. So 50% reduction in time means it's a great achievement, and it will be a great for the search operations. So I mean, repeatedly we can do the search operations. Yes.
Sir, I have a question. Sir, can we not follow a state machine based approach over here, where, as you said, the process needs to be automated, so that the precharging we do not have the necessity for precharging anymore. So can we not develop a state machine which automatically every time that the part of the cycle arises, it automatically sends a control to get the same done?
Yes, we can. So what you are talking about? Talking in the range of gate level, because whenever you are doing the state machine state level, so that would be, and now here at least I am talking about the in the CMOS level. So I'm not sure either state machine. I mean, that concept that could be introduced and that could be done, and conceptually it is the same way we are doing what you have said, but in the CMOS. Yes, it is possible. And whatever we are doing in the state machine, I mean, from one state to another state, when it will be going, and before that state, we have to, like our water pump. I mean, in our flat, every day morning we have to pump it, we have to recharge it. then only you would be able to use it, I mean, whole day. But whole day we have to use. So that is what we are emphasizing, that you do something. That here they are doing recharging, means loading the water, and they are using it and again loading. So here we are saying no loading, unloading, only search, write operation and search operation, only logic transfer. So in CMOS, logic transfer and in the state machines, how it would be implemented exactly I do not know, but yes, the concept wise it could be done. Okay, so this is just one model. I mean, from this one you won't be able to understand, because this is very specific. Just to show you, I mean, this is just one model, one design, one specific design, our own design. All these designs are there in our IEEE papers. So whatever I am discussing, I mean, CAM related, all of you can check it in IEEE papers. You can search with the CAM. So many papers are there. So this is one. And here, basically what I have shown here, this is the problem of my precharge free CAM. So whenever we are doing precharge, I mean, whenever mismatches are there, I mean, then mismatches are identified and it is grounded. And in case of left side circuit, only one red dotted line. Then the next circuit, 2 lines are there. In the next circuit, 4 lines are there. So means so many grounds are not good. So many discharging paths are not good for any circuit. So many charging paths are also not good for circuit, but some parallelism is required. So I mean, I hope you have heard about current mirror current. Anyway, so this kind of approach, but here is a problem, but we have made it, I mean, precharge free. And in some literature you will get, I mean, in IEEE paper also, and in conference paper also you will get it. But those they have claimed this is precharge free, but those are not exactly precharge free. Those could be charged self precharged. So we have to be a little careful whenever we are extracting data from internet sources, from any specific. So I recommend to go through some good journals, please. So, and all the terminologies. Research problem 4, faster lookup through masking. So faster lookup through masking means whatever we have utilized that the masking, we can go for global masking, we can go for local masking, and during using that masking we can means masking means what? Means out of, let's say, A and UP. So if we are masking U and P, means U and P no need to search. So you will only look for A and P. So no need to search means it is saving some power. And if it is searching only for AN, means it is searching 2 bits out of 4 bits. So it will be saving power. So faster lookup. So most of the time, whatever in computer, anything, whatever we are doing, most of the things, those are in the memory, those are in the lookup table. So if we are able to go to that specific table or specific row in a faster way, then computer would be faster, memory location identification would be faster. So let me conclude with this 4 problem. Another, so many problems are there. So if, I mean, teachers, if you wish to work on this specific area, and let me tell you, I mean, ample opportunities are there. And if you like to discuss with any problems with me or with any one of my students, I'd be happy to respond to you. And good opportunities are there in this area. So some of you may think of, and if you are thinking, and the way sir said that with that timing, with that machine, and we are now planning actually some AI that is to be introduced here, some hardware, software we are going to mix up with them, so that software and hardware that could be combined. I mean, hardware already we have fabricated. Testing is not done yet with SCL technology, but in future also we'll be fabricating with TSMC or TSMC with TSMC. But again, I'm funding everything. Those matters are there. So this is all about our I mean something, not all about, very few things on content addressable memory, whatever we have done and I have shared with you, and I do not know how much it will be beneficial to you. So you please look at, I mean, if something, if 1% you find it beneficial, if some people are working, then that would be only for me, for you. So and conclusion. So this is artificial intelligence. What I told you, we are going to introduce, and in 26 nanometer we are planning to make one memory. So let me see. I do not know. It will be depending on my scholars also. So some references, very few references, but actually I have taken around 50 references for this. Material, and these are related publications. What I talked about, these are all related publications, and mostly are from IEEE. I mean, all are from IEEE. So these are good. Hopefully these are good. So still, if you find any problem, any other scopes, options to introduce something new into that, then definitely it will be good. So the research community, I expect something that to be added on top of this. So thank you for your patience, and it was good to some of you at least ask some questions, and I hope and if I have said something, I mean, lightly, that is for the analogy purpose, please do not take it otherwise. So that's all from my side. If you have any questions, please.
Not a question, but a direct feedback, sir. Kindly allow me to. This is Magnonil Goswami here, Dr. Magnonil Goswami here. Sir, first of all, thank you very much for that beautiful analogy. You know, like, I hope that the NAND and NOR thing I would never forget in for the rest of my life because of that analogy of yours. So heartfelt thanks to you, sir.
No. So many analogies are there. I mean, now, I mean, in old days, I mostly am from Calcutta and Jadavpur University, and so many things. Then every time I am trying to give in memory in terms of library, in terms of, so this momentum I learned it from my beloved teachers, and believe me, some old teachers, they are tremendously. I mean, now the only people are fascinated with IITs. I mean, in some old, like Jadavpur and Calcutta University, oh, they are tremendous, really good. I mean, one of my teacher, you know, why modulation is required? Why modulation is required in communication? Why modulation is required? Do you understand why modulation is required? Goswami?
Hello, sir. Can you hear me?
Yes. Why modulation is required?
Sir, modulation is required for better packing and to avoid loss of, loss of contents.
Okay. So I'm giving you one analogy. Let's say, so would you mind? I hope you are young. Goswami sir? I hope you are young, right? Or aged? Am I audible, Goswami sir?
Sir, I missed the last few lines, sir, actually.
Okay, no, I can't say. No, Goswami sir, are you, I hope you are young.
I am, sir. I am like a student of yours only, that's how.
Okay, no, it's okay. No, you just listen the analogy and you will not forget. Let's say, I mean, normally, you are from, sir? You are from?
Sir, I am from Jalpaiguri, West Bengal.
Oh, no, you are from West Bengal. Okay. So you will be knowing. Hey, 2 minutes. Gotcha. I mean normally, I mean during our student time, we used to use bus for travel from one place to another. So normally, whenever young period in Dadapur University, whenever we are traveling by bus, so many young girls are there also. And let's say if you have entered into a bus and one girl is sitting in front of you, and constantly you are watching to the towards the girl, right? So, would you be able to convey any message? Constantly you are watching. Why you are watching? Nothing. And constantly you are watching the girl. So, no message will be conveyed. So, whenever, वो जो गाना है ना, आंख मारो तो something, whenever you are modulating your eyes, then you are spreading the message. What you are trying to. This is the need of modulation. So without modulation, message cannot be sent. And modulation, and whenever we are having bad habits, now whenever we are talking, we are moving our hands, we are moving our legs, we are moving our body. These are actually we are trying to modulate, we are trying to convey. Along with the words, we are trying to convey something. We are sending the signals. I mean, that is the primitive signals. That is where the modulation is required. So एक बार आंख में modulation हो गया, then एक बार आंख में थोड़ा disturbance हो गया, then it is the modulation.
Fantastic analogy, sir. Sir, even you mentioned about artificial intelligence. So in that regard, let me draw a small example. Actually, this is called zero knowledge proof system, ZKP. ZKPs are, it is used in, even mentioned about ATMs and all these transactions that are taking place nowadays. This is where lies the, ZKP is being developed by various organizations just to ensure, security. Now, the point why it sounded so relevant, they are, two people, they interact with each other without sharing anything actually. So you made me think of that thing, when you say that, if you do not modulate your eye, you cannot convey the information. That switching of eye is at least required, sir. Yes, it is. Yes. Even in zero knowledge proof.
Okay. Yes. True. So any other questions? Any other thing? Please, if anyone else, if any other question is there, please. Okay, so Kullan, if anyone is asking for my emails, I hope if you need for any clarifications, for any further or any research, anything, I'm active in internet. So if you are sending me any mail or anything, definitely within I'm sure within 24 hours you will be getting reply back.
So may we have your email address, please, sir?
Yes, my name dot my title @gmail.com or @nitm.ac.in. So Anup, ANUP. So this is in the first slide. It is there.
Okay, sir. Please tell me. I am sharing it in chat box if possible.
Sharing what?
Is it mentioned in your PPT, sir?
Slides, yes. In my slides also those are mentioned.
Okay, sir.
So I hope you will be sharing the slides with the participants, so yes, they will get it. And nowadays, no need to write. All of you will get it. If you are searching with my names, I hope if 100 publications are there, I hope you will get my name and the email. Okay, this is the mail ID. This is my personal one, and if you are writing nitm.ac.in, you will be getting my institute email ID. So anyone, anywhere, if you are writing, and you'll get me.
Thank you, sir. Thank you very much.
Okay, Kullan.
Okay, thank you, sir. No, sir. Thank you, sir, for your valuable talk, and I think it is so much informative talk. And sir, each and every topic on your low power, low cost memory design, so you are correlate with practical example. Each and every topic, sir. It is fantastic, sir. Fabulous. So,
Thank you.
from our department, Electronics and Communication Engineering, NIT Manipur, sir, we'd like to thanks for your deliver such type of lecture. Thank you, sir.
Okay, thank you, Kallan. So, may I leave, Kallan, or anything, any other?
Yes, sir. Sir, if possible, sir, please share your PPT. Then I will share to all our participants.
Yes.
Okay, sir.
Within
Okay, thank you,
10,
sir.
15 minutes, by today
Okay.
only, I'll be sharing it with you.
Okay, no issue, sir. Thank you very much.
Okay.
Okay.
Okay, Kallan.
Yes, sir. Thank you, sir.
ঠিক আছে কল্যাণ তোমাকে একটু দেখি আদার পার্টিসিপেন্টস আর দেয়ার অর কল্যাণ ইফ ইউ সুইচ অন ইউর ভিডিও
Every participants are there, sir.
Okay. No, do you have a next lecture from 12?
Yes, sir. Right now.
Okay. Thank you, sir. Okay, I'm leaving now.
Okay, sir. Okay.
Thank you, sir.
Madam. Thank you, madam.
Thank you, sir.
Dear participant, please mute your mic. Welcome, sir.
Yeah. Welcome, Dr. Mandal. I have joined.
Yes, sir.
Yeah.
Okay. So, shortly, we are starting our next session. This is our final session of 5 days faculty development program. So, welcome, sir, Dr. Prakash Tiwari from IIT Jodhpur. So, Sri Prakash Tiwari joined IIT Jodhpur in May 2011, where he is currently working as associate professor in Department of Electrical Engineering. Prior to join IIT Jodhpur, he worked as a postdoctoral fellow at School of ECE, Georgia Tech, Atlanta, USA for 3 years, from 2008 to 2011. He had received PhD in 2008 from Department of Electrical Engineering, Microelectronics at IIT Bombay. During PhD, he had also worked at NTU, Singapore. Dr. Tiwari is a senior member of IEEE and Vishweshwara Young Faculty Research Fellow of Ministry of Electronics and Information Technology. His research includes development of high-performance organic FETs, sensor and RAM devices for flexible electronics. He has published about 100 research articles, including more than 50 in peer-reviewed journals of high repute, such as Organic Electronics, ACS, Applied Materials and Interfaces, Applied Physics Letters, and IEEE Transactions of Electron Device. At IIT Jodhpur, he leads the Flexible Large Area Microelectronics FLAME research group with focus towards demonstration of flexible device and system for eventual biodegradability and green electronics. Thank you, sir, and welcome for your active participation in our FDP. So over to you, sir.
Thanks, Dr. Kalyan Mandal. It will be around 1.5 hours or 1 hour, whatever I'll discuss, and in between I can be interrupted. Okay.
Okay, sir.
So thanks for the introduction, and I'll share my slide now. Let me. So let's see if it is visible to
Yes, sir. Yes, sir. Is it?
all of you.
Yes, sir. It's visible, sir.
Yes, sir. Visible, sir.
Okay, fine. So
Okay.
good afternoon, and okay. So the title of my talk is Design Aspects of High Performance Organic Thin Film Transistors and Circuits. So essentially these are type of transistors which are made with organic materials, and they have applications in various other areas. There were other topics which I'll not touch into, which is resistive ramps, but mostly organic semiconductor-based devices I'll speak about. And as Dr. Mandal said, I'm kind of leading a research group which is called FLAME Research Group, Flexible Large Area Microelectronics at IIT Jodhpur. And specifically, we work on kind of alternative devices which can help the environment rather than changing for high performance and other aspects which are anyway being done by inorganic community, which is silicon. So in introduction, I'll just talk about why are we thinking about this. So why do you need to think about organic devices? Why at all organic? Why not just high performance and everything? Then why this is flexible and why flexible is important. And then I'll talk about designing high performance. Now, designing means this is not a conventional VLSI or system design. It's like even designing a device with new material is a challenge to get high performance from that. So that process development part I'll discuss about. And for any flexible device, you need to talk about if this is flexible, you bend it, what happens, or if you bend other way, what happens to the device. So that is called electromechanical stability, is a term where not only bending and mechanical stability and flexibility, but once you bend, what is the electrical performance of device after that? So this all together, electrical stability along with mechanical stability is called electromechanical stability. Then there is a term recently people are talking about green processes and green electronics. Now, what is green? Green is more like soothing to nature, and green electronics is more like which helps or not at least causes problem to the environment. That is called green electronics. So to make anything which is called green electronics, you need to have which is something which can be biodegradable. Now, a silicon or anything made on copper or conventional rigid substrates cannot be biodegradable. So you can think about something which is made on substrate like paper or other polymers which can be dissolved. And going towards more nature-friendly electronics, you can also think about in place of hafnium dioxide or silicon dioxide, can we have something which is nature-inspired dielectric? So those kind of materials will be explored, and very smart applications will be spoken about. One other aspect, like these devices could also be helpful in sensing some parameters. So I'll discuss about some kind of off-the-track applications of this organic FET, and then I'll summarize. Okay. And in this picture, you see example of something called a flexible electronic device, which is demonstrated by a company called Xerox. So this is just for the sake of showing it. Okay. To start with, see, we talk about electronic products, electronic systems, and eventually we say not only mobile phones or our TVs or computers, but in fact everything, the fridges we use and everything. If you see, each product has a timeline. Our washing machine, wherever electronics is there, it could be timeline, could be 2 years, 5 years, 10 years, or even 20 to 30 years, depending on the product. But there is a time when whatever you do, how many ICs you change, how many electrical connections you change, you see this device not working and that electronic product not working. And that is the point when you think what to do is this. So you certainly go like a fridge you sell to a garbage collecting person or somebody who is like buying these things. You just, okay, take it in maybe 1,000 rupees, 500 rupees, whatever. And now these are the same thing you do. So either you throw it in dustbin or you throw in some places you think that it will be recycled, right? And then you give it. And even forget about individuals, even governments do not have policies to completely recycle any of the things which are throwing, right? So eventually it just creates electronic waste. And that is a very serious concern, which is in last couple of decades, that is causing serious concern, not only for India as kind of developing country, but whatever developed countries we see, they all are suffering from this e-waste problem. Because every 6 months to 1 year, people are changing their smartphones. So that is one electronic waste. And TVs, every Thanksgiving, they try to change the TV, and that goes to your their near big dustbins, what they have. They just, and some people take those TVs, but many of the cases that again goes as electronic waste. Those electronic wastes are collected, they go to some place and they try to kind of recycle it. In countries like India, sometimes it is segregated. You segregate the electronic waste.
Yes, madam.
And then many times what happens in Noida, in Delhi NCR, you see there are landfills. And landfills are the places where they start dumping all these garbage. And on the top, they try to put something and just try to put some green grass and something. But then eventually it's a garbage which is going in the earth, and it will eventually contaminate and pollute everything. So first thing, we do not know how do we dispose these e-waste. But anyway, so this problem is there. We all have to understand that. But can we reduce this effect? And that is something as researchers one can think. So there is e-waste. Now, as individuals, you can keep thinking about, can we reduce this impact on the environment, on landfills, and in any water flow path it is going, and it is causing the problems. But in fact, country itself had realized long back, a decade ago, and first e-waste regulation came in India, you say in 2011, and 2012 it became functional, and it was amended later also, 5 years later, 2016 and 18 it was amended. It means countries had recognized that we are generating a lot of e-waste, and several further developments had happened. And recent, this October 2020, you say clean to green awareness. And so e-waste roadmap is also available for India to just take care of this problem. As users, we never realize that these things are happening. But anyway, now why this area is connected? So as a researcher, you think that can we do something to reduce this impact effect? So you say, what if some of these products which were showing on the earth, what if some of them were lighter? And moreover, what if while making themselves, even when you make these products, a lot of temperatures, high temperatures are used. So while making, if you produce these products at much lower temperatures, then it could further help. And many times when you throw something rigid and think about in a water flow path, a rigid product is there. And what one rigid product does, it just tries to accumulate many other waste items, and it chokes it, right? So paths are choked. So in place, if there was a flexible e-waste, probably it could have gone through some path, but if it was rigid, it just chokes it there. Further, forget about rigid and flexible. If it was biodegradable, it was easily dissolving and again going through it, right? So this could have been more friendly toward. So all these terms together, people call it organic electronics. And organic, the word is used in food and vegetables and other things. In chemistry, organic is used. But then organic and green electronics, if you see the holistic term, it's more like friendly electronics. But then one thing is, you just think about organic electronics where products are less harmful, they are flexible, they could be biodegradable. But then nowadays, when you produce electronics with organic, and if it is not functional, if it doesn't help you to achieve current scenario of things where you are talking about Internet of Things, where everywhere you want sensors, you want signal conditioning, you want data transfer, you want decision-making devices, you want storage. So if there is electronics like that, if it is doing kind of decisions, it means you need transistors. If you want sensing smartness, you need sensors. If you want something which is storing, you want memory devices. You for smartness, you need all these things. So can they be suitable for intelligent systems? That is a question. Certainly they will be. And then along with having the advantages of their low cost, flexibility, their process simplicity, low temperature processing, and large area processing capability. So all these are kind of aspects of this area. And what we do here is we try to work on various devices, and some of the pictures you see here are of transistors and RAM memory and other devices produced on flexible substrates. How this technology is moving for anything which is flexible, eventually one also thinks that if it is something flexible and when you are using organic materials, then you talk about solution processing. Now, when you talk about solution processing, there is something called printing. And you can, if you want to make a structure, you make that structure by printing. And now if you print something for electronics or transistors, you print, the term comes, which is for industry, it's more like printed electronics. So electronics which you print, conventional electronics you make by VLSI and CMOS technology, where lithography and rigid things and all those foundries are there. But something if you produce by printing, that is called printed technology. So this technological trend graph shows the devices which are done by printed, and it is of last 10 years, where you see a lot of amount of printed electronics is done for organic light emitting displays, OLED display. Now, where do you find this OLED display, which is organic light emitting diode, means light emitting diodes made by organic materials, which are printed. And even if you see right now, you say OLED TVs. OLED TVs, like in place of LCD, you have organic light emitting. It means organic materials are already finding its place in displays. But then any display, anything which you glow, there has to be a backplane circuitry. Now, if this backplane circuitry also you make by organic materials, then this could be a fully organic or printed technology. Now, if you focus on circuits which are made by these organic transistors, this plot is again taken from a reputed journal paper, which is Advanced Functional Materials, published in 2020. What you see here is on x-axis you see time, how things are reported with time. And on y-axis, you see voltage normalized frequency. It is again a speed or performance parameter of a transistor-based circuit. Now, why voltage normalized frequency? Because in general, you apply high voltage, you will get higher current. And higher current means better performance, right? So voltage normalized is like you want to compare things on the same scale. So you normalize with voltage. So you say megahertz per volt. So voltage normalized frequency from ring oscillator, which are very simple devices. And then you see vacuum evaporated semiconductors, not solution processed, are compared. And here, if you see these blue dots are on rigid substrates, which are silicon or glass substrates. The red ones are done on plastic substrates. And green in recent years, you see they are on paper substrate. Paper substrate means you want something which has a capability. If something is made on paper, paper will be eventually degradable. So obviously, this goes towards biodegradable electronics. Now, application for smart systems, how can this technology be applicable, which is based on essentially solution process materials, or materials which can eventually be solution processed? Then there the 3D printing technology also finds a place where you can say 3D printed devices can be demonstrated, where source, drain, gate, everything can be done by printing. And hybrid integration, where devices coming from various technology you can embed together. And what could be these potential devices? Obviously, transistors could be there, resistive random access memories could be there, transistors, sensors could be there. Even you can talk about batteries, which can be printed. And what could be subsystems? Subsystems could be, say, smart textile, where you have a smart cloth which is which is sensing various things, which is trying to harvest the energy and so on. Electronic skin can be there. Other robots which are being made, they need some skin, right? But that skin has to have functionality of, say, temperature sensing, force, flexibility, stretchability, and all those things. So those kind of things can be called e-skin. And with this technology that can be thought of. Then health monitoring patches. There could be simple patches which you have on body somewhere, and they're just trying to check your physiological signals and they can communicate. So these could be some subsystems which can be used and demonstrated. But then one thing you have to understand is organic electronics is a complementing technology, which is which is, it just complements the existing technology by giving patches, e-textile and other things, but not going to replace your conventional ICs, which are you are designing for computers and MOSFETs. So they will always be there. They can be smaller, but then if you want something which is on large area printed thing, that cannot be done by silicon. So that is where, or maybe e-patches, electronic patches, that you cannot make by silicon, right? So there you want soft material, soft electronics. So that is where this organic electronics will be useful. And this is coming from some literature where you see side by side, one picture you see which is conventional silicon based electronics, where you have a PCB and then all the ICs stick together. On the other B and C, what you see there is something which is a patch which is pasted on the skin. And this is what we expect, where something which is fabricated on a flexible substrate, and then interconnects also, if you see, they are designed in a way that some stretching, some deformation still make sure that it is intact. Okay, so it means they can be also conformal, they can be used on various curvy linear substrates, they could be bendable, stretchable, rollable, but those things cannot be done by conventional rigid electronics. But when you design these kind of systems, even you cannot use just straight line metal interconnects for this system. So there also, when you say something is stretchable, means you have to give it a flexibility so that even if you stretch, the actual length of the connection increases, but still doesn't break. So if you have a pure straight line, if you stretch it, the metal will break. But if you have some helical or some kind of spiral structure, probably it can still be stretchable. So these kind of thoughts are always embedded in any skin-like electronics, which is thought of ever. But for more broad perspective, you say essentially you want something to be made by this flexible electronics, which is a receiving end, which is sensing and input. And then eventually at application level, what you want, they could be relevant to your cloud-based Internet of Things, where you sense something. Frequency could be much smaller, but still it can transmit the data somewhere, and that could be used in, say, real-time applications, real-time health monitoring, or real-time decision-makings, and so on. In between, you can think about wearable systems, prosthetics, robotics, something which is implantable, somewhere where printed batteries are energy harvesting, and then communication modules itself on flexible substrates. So all these things, and this is taken from a 2018 article by Professor Ravinder Dahiya, which was in NPJ Flexible Electronics. Okay, so this is a very good overview of this whole thing. Then one thing I said, there is a possibility of 3D printing. So this flexible electronics offers. Now printing you do, generally you don't do printing on rigid substrate. So even if you think about your inkjet printers, when you print, you want A4 sheet has to be quite flexible so that this printing happens. You cannot just put a glass A4 sheet to be printed, right? But certainly, so you want something which is flexible, it gives suitability to printed electronics. But then if you are able to print multi-layers, and not only a multi-layer for a single device, but multiple layers of devices, that possibility is given by this printing. And when you have the capability of printing multi-layers and multi-layers of devices, then you have option of this 3D integration. Okay, so that also, it's again this report is from 2019, where circuits were demonstrated by 3D printing, and you can see this picture where source, drain, gate, semiconductor, everything were printed on flexible plastic film and stacked in like 3 layers of transistors. Now this also saves you area, but then this gives you functionality, capability of multi-layer printing. So this is, again, this adds a new feature on flexible electronics. What could be future systems of interest? Now, this is from somewhere, again, where people have just tried to show that conventional electronics is very cumbersome. If you want to say read the signals of body or sometimes brain, you have to have multiple number of electrodes. For example, here you see so many electrodes on the brain to actually trying to read some signals. Now imagine something which is not so many electrodes, wires going on. You have a cap which is more like stretchable and flexible, and you can just have directly on head. And these wires will be essentially metal lines running on that cap itself. And then you can have a module where all this data can be stored, and that is transferred directly through some wireless module rather than these wires directly going somewhere. Now that can be a very smart way of doing these things, and that can only be possible when you make these things through flexible electronics. So this is one something which can be called future system of interest. In any case, whatever systems you design, any electronic system, be it flexible electronic system or rigid electronic system, you have to have some essential components. And what are those essential components? One thing, you have to have application-specific integrated circuit, means ASIC for that particular operation. And along with that, you can have some microcontroller unit. Then if system has to be smart, the system has to have some sensors, right? It has to sense anything. So sensors are one component. Then on the other hand, whatever data you are generating, that has to be stored. So you have to have memory component. Now memory essentially has to be non-volatile memory. Means whatever you store, that has to be there for longer time. When you do all these things, you want to have some battery or power. Okay, so you need to have power management unit or battery. And if you don't have battery, you might need energy harvesting mechanism where supercapacitors are probably solar cells and so on. So all these things are essential components for any of these current electronic system. And this is just one IoT driver, but I'm saying any smart system should have these 6 components essentially to make it smart, where it can be energy autonomous, it can be movable, it can be handheld, but it has to have ASIC and MCU, it has to have some sensing element, it has to have a connectivity so that data can be transferred. And devices could be obviously printed batteries, supercapacitors, solar cells, and related circuits. And then obviously transistors, sensors, RFID, and RFID is again a radio frequency based antenna and tag. So these systems could be very useful. Now the people who do design, try to design circuits, for them it's a new thing. Like, okay, MOS technology is there, MOS parameters is there, you have process development kits. You can do almost all the design based on whatever your synopsis or other tools give. What happens if you make transistors from a technology where you do not know about materials? Okay, you do not know about structures, what structures you are using. And there you have source drain which is being doped, which is formed by doping something N plus source and drain. But here if you just try to see, there are source drain which are directly metal lines. Now because of these differences, the design or PDKs cannot be same. So are there way to design systems based on these devices? So people have tried, and there are some explorations available. The important thing for designing using these devices is whatever devices people fabricate, they have to characterize it for output and transfer characteristics. So first they have to characterize for basic discrete device parameters, which is output and transfer characteristics and related parameters you extract. And then for circuit related thing, at least some CMOS inverter and ring oscillators should be fabricated, and with time, so that you get rise time, fall time, and all those things, gain. So circuit and device measurements one has to do. And based on that, one has to develop compact models, device compact models. What are device compact models? Everything starting from threshold voltage and parasitic capacitances and everything, so that eventually you know if this device is used in a circuit, what will be the speed. Okay, so first thing is you obtain device characteristics through electrical characterizations. Then you develop PDKs, process development kit. And once you have that, then you can start using standard tools like Cadence, Virtuoso, XSpice, or any circuit simulator using those compact models. And then you can follow this design rule check and array design, layout design, and you can simulate and come back. See, this whole process can be done only, so devices are important, compact model is important, and then any circuit simulator tool can help you in design. So you have to follow standard procedure for design. And then once you design it, then whatever technology helped you to make these devices, you print the circuits or systems with appropriate material or 3D printer. So this is your eventual goal, where this kind of technology, if this is design is done, integrated circuits and ASICs based on this, then this has to be followed. But what are the challenges? Challenges are, say, for a device A where material A and B are used, and device B where material C and D are used, the compact models can be entirely different. It means there are not any universal models. So every time, every laboratory or every company produces a new device with new material, then you have to get PDKs for that device in that technology. Okay, so that is a challenge in any systematic design for flexible electronics, but on the other hand, it has a lot of scope of learning and contributing. Okay, so as I said, organic electronics is a complementing technology, and it has some advantages like low cost, flexibility, process simplicity, low temperature processing. But one can always ask, can we not compare? You are just getting the advantage of flexible, but silicon could also be flexible if you have amorphous silicon or something closer to that. You don't need to have crystalline silicon. So one thing is crystalline silicon, the mobility numbers are hundreds. But the moment you go to something like polycrystalline, the mobility, what you get from transistors is lesser, which is 50 centimeters square per volt. And similarly, if you go for a more flexible version, which is hydrogenated amorphous silicon, this gives you 1 centimeter square per volt. Now, why from polysilicon to hydrogenated amorphous silicon? Because polysilicon is deposited at 600 degrees centigrade. Now, if you are thinking about this kind of semiconductor on any flexible substrate, 600 will not be suitable for any flexible substrate. Then people spoke about hydrogenated amorphous silicon, but that also is deposited at 300 degrees. So it means though flexible devices can be made, but then these temperatures, very few substrates can withstand these kind of temperatures. On the other hand, organic semiconductors have shown the same numbers what this amorphous silicon has shown, and the processing temperatures are much lower, which is like 100 degrees centigrade or lower. So that is one advantage which organic semiconductors give when you go for flexible electronics, which silicon doesn't give. So the summary is organic electronics can fill the gaps where inorganic cannot be used. And these transistors have shown potential to be used in circuit. Now, one of the very basic circuit what you think about from this can be your simply, as I said, organic light emitting OLED displays or OLED based TVs. So essentially they are light emitting diode. Now any light emitting diode to glow, you need to supply a driving current. At a certain current it will glow, right? Now where does this current come from? Current has to come from some driving circuit. And this is what is shown here is a schematic of your a basic driving circuit. Now what you say, there are a couple of transistors which help you to get this current. Now what do you want from these transistors? Essentially you want two things from these transistors. One, say this display can be static or dynamic. So if you want this display to be static, transistors performance should not change over the time when you fix the applied voltage. And this kind of stability is called bias stress stability, Second thing, if it is dynamic display, something where display is changing, then what you have to, you can think about multiple times operation when you switch on the same device for multiple times, switch on, switch off, switch on, switch off. These characteristics, IV characteristics should not change. So this is called multiple repeated switch. So these are the two essential, along with obviously high mobility and low voltage operation. You want these kind of bias stress stability and repeatability. These are essential from any device. Okay. Now, if you want to design a very good transistor for circuit and sensing, what are the parameters? Okay. So essentially, to design any good transistor, the challenge is to get high mobility, low voltage operation, and contact resistance. Now, where does this contact resistance come into picture? Because in silicon, we are rarely talking about contact resistance. But here, since source and drain are directly deposited metal, and any metal will or may or can pose a contact resistance or Schottky barrier with semiconductor. And you can call it metal semiconductor Schottky contact. That contact barrier can result into something called contact resistance. Okay. Now, operational and environmental stability. So, operational stability, we said bias stress stability and repeatability. But environmental stability is what? Once you fabricate devices from these materials, are they stable in environment? Are they stable when humidity is there? Are they stable when high amount of oxygen is there? Are they stable when you apply high temperatures and so on? These are called environmental stability. So these are for transistors. But if you talk about sensing, then what is the sensitivity for a particular aspect? So that you have to see. But then what is good thing about these transistors which are made with organic semiconductors? One thing we have seen that the model of current is very identical or very close, matches very closely with the one we get from conventional MOS devices, which is your IDS is half mu Ci W by L VGS minus VT. So it means that current level, the model is almost similar when you just try to see the current output and transfer. That matches with this current equation. Hence, it becomes easier for you to estimate something called mobility, field effect mobility. And Ci we already know, WL we already know, VGS we apply, and VTS we can extract. So from this current equation, we can actually extract various parameters after characterizing the device. What is the way forward? Way forward is, if you want high mobility, probably you can search for newer materials with better charge transport. Or you think if lower mobility is coming from bad dielectric and semiconductor interface, or metal and semiconductor interface, then you think about dielectric and interface engineering. So you have different dielectric layers, and you talk about better interfaces. Then contact engineering is where you think about if there is a Schottky barrier, can you eliminate this Schottky barrier between metal source drain and semiconductor? And then you can think about overall design, where do you put source and drain, whether in the bottom or on the top, then you encapsulate it. Now from saturation current, when you characterize these devices, you can always, from transfer curve, you can always get something called sub-threshold swing. Now from that sub-threshold swing, how faster this switching and switch off, switch on happens, that can help you to estimate something called interface trap density. And you don't want high interface trap. So that is called DIT, and that can also be estimated. For bias stress or electrical stability, we have done some basic modeling where which time you record the drain current. And at time 0, there is a drain current which is called IDS 0. And then you can find that there is exponential decay in most of the times. And that can help you in model this bias stress decay if there is any. But then what is this bias trace? You say constant bias you apply at a particular fixed gate and drain voltage, and you measure IDS with time. Okay, and that model we are talking about. Then what is multiple transfer curves? You just try to characterize the device multiple times, you switch off and switch on, and you just record the whole transfer characteristic. Now for sensing, what do you do? So for sensing, say if you want to sense light, so you are characterizing the IV without light, you characterize with light and see the change. Similarly, if you want to change the humidity, so if you characterize during higher humidity and without humidity, so that is humidity sensing. It could be anything. So this is how you use these devices for sensing application. But then say, for example, if you are talking about photo sensing, then there has to be also some parameters which quantify what is the amount of photo sensing. So in that case, you can say photo responsivity and current modulation. What could be photo responsivity? Photo responsivity, if you say it is R, so you can say current when photo or light is shine minus current when device was in dark. So I photo minus I dark by A into Pi. Now what is this Pi? P is coming from I photo minus I dark by I. And so this photo responsivity can also be calculated, where R is I photo minus I dark by A into Pi. So you can also think about effect of bending. What happens when these devices are bent? So when you bend this device, there is something called strain. So there is a strain which is applied on the semiconductor. Now this strain can be compressive or other way. So two kind of tensile and compressive strain can be applied. So that percentage is actually estimated by thickness of substrate. Okay, and thickness of substrate you mostly know. And there is something called bending radius. Okay, so bending radius you apply, and from that you can say strain percent is T substrate by 2 R bend into 100 is strain percent. Now with strain percent you can always try to find how the performance is. Well, just give me a moment. Okay, fine. So what we learned for photosensing, you can have R and P. Now P is modulation and Pi will be intensity of the light, which is kind of so it could be UV light, it could be any other light. So these are the two parameters, and then effect of bending, and finally what I said, there could be electromechanical stability, where these both things together you are kind of trying to see what happens. Anyway, right. So contact resistance we discussed about. What is this contact resistance, which is not there in the conventional devices? Now contact resistance is coming from energy barrier. Okay. Now this energy barrier between source gate to semiconductor, you have to know what are the levels which we are talking about. For organic semiconductors, for example, for silicon and other semiconductors, we know that we are talking about conduction band and valence band. Whereas in organic semiconductors, since they are not crystalline semiconductors, you have something called lowest unoccupied molecular orbital, which is LUMO, and highest occupied molecular orbital, which is HOMO. Now, LUMO is something like close to conduction band, and HOMO is something which corresponds to valence band. Okay. And metal always will have a work function. Now, for N-type devices, because LUMO will correspond to conduction band, so electron transport will happen through LUMO. Now, for N-channel device, you have to see what is the barrier between this metal work function to LUMO. And for P-channel device or P-type of transport, you have to see what is the barrier between this HOMO and this metal. Okay. So it means there will always be a source to semiconductor barrier. Why do we call it source to semiconductor barrier? Because the injection of carriers happens from source to semiconductor and not from drain to semiconductor. You think about any device, there is a injection that happens from source to semiconductors, be it electrons or holes, and they are drained. They are drained at drain terminal. Okay, fine. So now it means there can be barrier even if you take gold. Now what we see is any metal which has a work function of 5 electron volt or so, they have very less Schottky barrier or contact resistance with P-type semiconductors, whereas for N-type devices, they can give you some contact resistance. Whereas for N-channel devices, metal has to match with LUMO. Now LUMO is generally 3-4 electron volt or 2 electron volt or 4 electron volt, right? But it doesn't go up to 5 electron volt. Now, if you want to get some metal which is close to LUMO, you are talking about aluminum and calcium. Now, most of the metals are oxidizable, or they oxidize very easily in the ambient because work function is very close to your vacuum level. So that is the problem. You cannot get good N-channel devices because suitable metals are oxidizable. Aluminum is a bit okay, but aluminum also gets oxidized. On the other hand, P-type devices work well because gold, platinum, whatever metals match work function with HOMO, they are stable metals. Okay. So these are some challenges, and people think about eliminating these, or people try to make devices with these stable metals itself. But then for N-channel devices, there is an issue of contact resistance at lower voltage. Then one can think about frequency of operation. Obviously, frequency of operation somehow relates with how faster your devices work, what is the mobility you are getting from devices. And for organic semiconductors, you get something like 0.1 to 1. And that is where your frequency is limited. So you cannot talk about very high frequency, something from circuits from organic electronics. Okay. So, but rigid CMOS transistors, there you can aim all the high frequencies because of mobility numbers are something like around 500. So there you get very high kind of numbers. But organic semiconductors, you are talking about 0.1, 1. So then frequency has to be lower. Okay. Fine. I think this slide had to be just not there. But anyway. So repeatability and bias stress, when we talk about, and many times we think that probably this could be problematic, but it's not like that. These are very old results, kind of when I had started postdoc and later. But then what I want to show that there is a capability where you make devices which can work at very low voltage and they can show very good bias stress performance. But many times this bias stress decay, we always keep worrying because now you see a decay and this is, you see a reduction in the current. But then to just have a kind of, to quantify this reduction, later we thought, let us define that this current should not go beyond 10% decrease. So we defined later a parameter which is called T10%. And T10% is the time or stress time when your device current changes by 10%. And then you can say that if your device has higher T10%, then your device is more stable, right? Because there is no standard. This is what we try to follow. And later, 5 years later, we also reported that many of the devices with vacuum evaporated, which showed very high performance in terms of this 10%. Okay. But we should not also keep worrying about this bias stress stability. It's more like if you keep working and if you get some rest, you are recharged. Similarly, bias stress stability is something where if you keep stressing the device, you see a decay, but many times if you just give it a rest after some time, it just recovers back. So your current is recovered and again you can stress and it is recovered. So right now, this is again some unpublished result of very old work, where you could see this blue dotted line is actual decrease trend. But then in bias stress, you see device is decreasing very significantly. So it's like 1 hour stress followed by 20 minutes rest. And in 20 minutes rest, you could see the current is almost reaching to its initial value. This was done on a rigid device. But then whatever models one uses for this bias stress stability, you could see that during this stress, it is following a model which was explained earlier. But if you give a rest, it is again coming back to the original one. So selectively, you can apply this model if there is a periodic bias stress. Okay. But most of these things were discussed on vacuum evaporated semiconductor. And the goal of the research community is just explore something which is solution process and also stable in the ambient. So one of the materials which we found long back was, again, pentacene was something which was widely explored and all the high performances. Today also people demonstrate with pentacene. But the only problem is pentacene is thermally evaporated. Now this structure which was actually modified pentacene, where you see actually some branches here, couple of branches, which are in pentacene, and this makes it solution processed. And then this material is known to show higher mobility, high stability, and low cost. And we had been working on this material since long, and we explored it for various process parameters, for various electromechanical stability, for other applications. So many applications we explored in last, you can say 5-6 years. So this was widely explored material by us. And we started with certain strategies. One was to improve the performance by phase separation. Now, what is phase separation? When you mix two things which are liquid, and sometimes they can just form separate layers. It's like you mix water and oil together, and whatever you do, oil just separates itself. So it means oil and water have an interface which they form, and they don't mix up. Similarly, if you do these kind of strategies where you mix dielectric and semiconductor, rather than depositing dielectric or semiconductor one by one, some cases you just mix it and deposit it, and they automatically form two layers. And in that case, since it is naturally formed, it might give you better interface. Rather than if you deposit one material, wait for some time, and then deposit second material. In between, other things like moisture and oxygen may come in between and may create an interface here. So this phase separation was explored, and what we found that vertical phase separation from the stiff pentacene and a dielectric which is polystyrene had resulted in increase in numbers. If you just talk about mobility, it looks like a huge increase. But if you just simply say process transconductance parameter, which is mu into Cox, because when you do this phase separation, even more dielectric is added, it means your Cox might be lower. So we thought, let us talk about mu Cox. That also was 3 times improved. And that was verified, and we worked on this, and numbers in mobility were showing like huge increase, but process transconductance increased by 3 times. So this was one first kind of start. One more thing, we played with various solutions also, but then at process level also. So various solvents also were explored. So a lot of exploration was done, and we got some good devices. Parallelly, we were also thinking to actually see this at simulation level, whatever we are doing, whether the same thing is corresponding in various simulations which we kept trying. and that was done parallel. So that there were some kind of modeling efforts which were done. We did change this temperature, and the same thing we tried to see if the same thing we are doing in modeling and simulation strategy. But anyway, I just talk about flexible devices now. So TIPS pentascene was explored in two flexible structures. One was simple ITO coated PET, which is a substrate, and ITO is indium tin oxide, which acts as metal gate. And we had deposited hafnium dioxide, which is a high K dielectric material, thin layer of hafnium dioxide, and then a polymer dielectric, which was polyvinyl phenol, PVP. And then on the top, we made this TIPS pentascene. And your so top source then was deposited on the top. Second structure, where we actually explored this vertical phase separation, where this is on hafnium dioxide, directly this polystyrene and TIPS pentascene mix was deposited, and because of phase separation, we got these devices. Okay. And see, these are all things like mechanical stability and interface traps, everything was studied. And we found that average field effect mobility in blend devices were higher. And in both cases, I think average performance was decreasing when you bend the device. And we just tried to correlate that when you are bending, the roughness of dielectric was increasing. And when roughness of dielectric increases, you get change in the performance. Okay, so that reflected in density of interface trap. Okay. So essentially, we demonstrated devices which were operating at 5 volt with very good output and transfer characteristics, numbers reaching up to say 1.1 centimeters per volt second, but average was 0.5. And then we did our repeatability and electromechanical stability, and not only in one direction, where cycles of multiple bending up to say hundreds and 500 cycles, where you give compressive and tensile both kind of strain. And then we tried to see these devices were quite stable even after 100 cycles of kind of repeated bending. So high performance devices which were highly reliable were demonstrated by this TIPS pentascene using TIPS pentascene. But obviously one has to also study what is the effect of TIPS pentascene and polystyrene ratio itself. And that also was tried. And there was, it's like found that 1:3 where TIPS pentascene versus PS were kind of much better compared to the other ones. And then that was demonstrated. So at that level also we did process optimization. Towards more application for biodegradability, as I said. We also try to see not only for biodegradability, what are, we developed this properly optimized devices and this technology, whether we can demonstrate the same on paper, whether we can demonstrate on any unconventional substrate, which is like plastic, Kapton tape, anything. We started with paper. Obviously, there were some planarization and other things which were required. And on paper also, we could demonstrate devices which were operating at 10 volt and with mobility of the same half centimeters per volt second, and which were very good at bias stress. They were very stable in humidity. Heat also, they were initial up to 60 degrees, they were fine, but higher than that, there were changes. And moreover, these devices could work in ambient without any change. So for 6 months, they were there in ambient. And actually, they showed long time air stability. Okay. So this is what we achieved from devices on unconventional substrate. This is efforts on paper. And not only efforts on paper, we also demonstrated efforts on something. This Kapton tape is generally we paste the substrate with the tape and we keep throwing this tape. Even this tape was a very suitable, because this is very thin and very flexible substrate. We demonstrated devices the same performance like 10 volt and up to 10 volt. And we could demonstrate these devices with both two type of dielectric, PV or PVP. And then we again explored it whether it is working well after in air for longer time. It did work well. So it was also long-term stable, and bias stress also was studied. Obviously, with time, this bias stress was showing more and more decay. So devices with time, when you see, bias stress was more degrading the device. Other than that, performance-wise, they were very fine. So these were some demonstrations of these transistors on unconventional substrate like paper and various plastic substrate. And these capture tape devices were also explored for their inverter behavior, switching behavior, and they were showing very good switching behavior. So you could see, but then one transistor, if you want to demonstrate an inverter, you simply take a resistive load and you change the amount of this resistive load, and you can see what gains you are getting. Obviously, this is a simple resistive division kind of thing. And then you see higher the load, better the switching. It's so this is what you get. Finally, towards application side, and as I said, this is kind of application of natural materials towards green electronics. We thought we will also will also apply some materials like which are gelatin. Okay. So anyway, so I want to have it just say I have some more slides to discuss, but maybe if there is any questions in between from me, I can just briefly discuss, and then I'll. So is there anything, any input, any feedback up to transistors on paper and plastic from the class?
No, sir.
Okay, fine. So anyway, so now we'll just try to have the second part, which is, so after this high performance transistor demonstrations, we thought let us go towards more see, you cannot go to complete biodegradable something. One is take the substrate which is paper, then everything is dissolved, it becomes biodegradable. Then individually you can, each component like metal, dielectric, semiconductor, you can think for natural and biodegradable material. And one material we found, which is gelatin, a very natural protein. And that we saw that has some smart properties. And one is simply when it comes in contact of humidity, its property changes. Okay. So then in that case, what was happening? We fabricated the devices with gelatin dielectric, the same device on ITO PET. And then we characterize it for crystallinity, then what is the leakage, then what is the capacitance density. Okay, so all these things we try to characterize. We saw that leakage was acceptable, transfer curve, repeatability, then we did our inverter characteristics. So first thing we explored where this device is working well for basic device properties and also for application in circuits, what is the stability. So gelatin, we found it was very good in transistor behavior. But then it's one unique property which we wanted to explore was humidity sensing. And here what we did was simply taking this device and using it as a real-time breath analyzer. So what we did was started inhaling and exhaling on this device, and then what we could see is the current levels were changing. So it means it was showing these changes in real time when you are breathing, and it acted as real-time breath analyzer. So this is one unique advantage for this, where these devices could show the performance which is which can be very useful in real time breath analyzing. And then this could have been something which this is in fact something which gives you the transistors get edge towards smart devices. Transistor one is switching property, you get some mobility, you get some on and off resistance and inverters and so on. And then other one is the smartness which comes from these natural materials. And one demonstration was this. There were other applications which were done earlier for photosensing. We were using these devices which as light sensing. And what are the most basic light components? You say you take some LEDs like red, green, blue lights, and you just for particular intensity you shine the light and see the changes at a very small level. You see these devices changing its current from off to on. You could actually see some switching. But then obviously for a one particular light, if they sense everything, then that cannot be called a good sensor. There has to be selectivity also. So some of these devices, for some colors, they were sensing much better way. For some other colors, they were sensing lesser. They had capability to be used as light sensing also. And then you calculate photoresponsivity and current modulation. And these numbers were, again, this study was published in IEEE Sensors Journal in 2017. So it had shown better R value for green. And then in this blue, you can see better P value, which is current modulation. Okay. But then OFET-based sensing, that was flexible. But it's like parallelly, there were a lot of other work was done on the material level itself, where you say one light is being sensed, but then can you just tune this property to sense other light, or can you just try to increase this sensing spectrum? Okay. So in that case, there were studies where we tried adding multiple layers of these organic semiconductors, and then also seeing what is the optical sensing performance. So in this case, you simply see sensitivity for red light is inferior compared to other ones, and these are just results where you actually see, if you see first set in neat tips pentacene or tips pentacene PS, both cases you say it is not sensing red color, whereas it is sensing blue color, green color, right? So, and UV also. But then on the other hand, so this was again presented somewhere in a good conference, actually NMDC 2019. But what one could see, can we just change this sensing band? Why not red color? If you want to sense the red color, can you do something? So in that case, other materials were tried with this tips pentacene. And one material, existing material, though it is not solution process, was CuPC, was tried with this tips pentacene. And then what was found is adding these materials, OFETs could sense all colors. So you can tune these organic semiconductor for sensing red, green, blue, everything by adding these layers. And then this again study was published in Synthetic Metals kind of recently, where you could see that for photosensing also there is a way to tune the sensing property by choosing suitable materials. And not only semiconductors, sometimes the dielectric you use also has impact on your device properties. And one of further explorations was done to use organic devices in storage or memory. And right now you can see very high voltage demonstrations only because right now we are talking about a dielectric which is 300 nanometer silicon dioxide. But then it's more like capability demonstration. So here you see molecular weight of dielectric also played a role in UV light sensing. Okay. So that was one study which was done. The last part which I want to discuss at this rigid OFETs here is there were demonstrations of memory behavior from these transistors, and what we showed that whatever memory operation happens, that can be programmed with UV. So generally there is a way to program with electrical pulse. So when you talk about these kind of memories, you program with electric pulse. But here what we demonstrated, if you program with electric pulse under UV, so either sometimes you program with ultraviolet or program with electrical pulse. Here, along with UV, if you program with electrical pulse, what we could see that we had increased the memory window. And at that level, at high operating voltage, we could see a huge memory programming conditions. And this is for non-volatile memory applications. Right now, the numbers are very huge because we are using this SiO2. But then what we can summarize it, photo is not only for a sensing parameter, but the energy which is coming from this light or UV can also be can also act as a enabler for this memory performance, where this energy could be used for programming in non-volatile memory applications. And what you see here, at least this window, if you see initial, what you see this black one, then programming with pulse in UV, you could see this red one. So it's like you can actually program with a much better window by this. So see, many of these studies later are more like initial studies where something is started and eventually it will lead to something which is more kind of quantifiable. But they were just starting points for some new study. But then this gelatin work, what we had done, was also very much appreciated by various kind of agencies, and also it was highlighted in Hindu and kind of tweeted the minister and so on, and also local news. It's so it was a wonderful work, and which is also we are trying to go ahead with that technology in more like smart real-time breath analyzer. So what I'm trying to say is there is a potential of this kind of technology to be researched well and to be applied for nature-friendly electronics. And obviously, this kind of electronics, you need to have materials. You need to have new materials, new semiconductors, and also you need to have more applications based on those materials. So if I want to summarize, I can say that high-performance organic transistors can be demonstrated with suitable fabrication and optimization techniques. Then devices can be produced on unconventional substrates, which are on various biodegradable materials and biodegradable substrates, also including conventional plastics that we had shown. Then one more feature I spoke about is if these devices are used as sensors, and one example I showed was say photo sensing, then I said this spectrum can be enhanced to sense various more colors by doing some reach compared to single layer semiconductor. And finally, we also kind of try to discuss where this photo energy or light energy can be considered as a good stimuli for UFET based on non-volatile memory application. So this is so all these, and there were many other things which could be discussed, but I wanted to make it more short due to the time duration which I'm talking, and between lunch and you, I didn't want to make it completely 2 hours thing. So that's why I tried to make it short, but I wanted to make it more like a to instill a thought process in all of you that see those silicon electronics and all the ADC, DAC and ASIC design, everything is going on. But there is a potential area where people should also look into, not only for high performance and not only for going behind industry jobs, but some research area which is which eventually could lead to more sustainable electronics or green electronics. So this is something. But then along with that advantage to nature or sustainable electronics, there is certainly a potential to be used in health monitoring and biomedical application. Why so? For example, I said breath rate analyzer. Now, the frequency of breath is so low that you actually don't want something at a very high speed, right? Because this breath rate is so low that these organic devices could be fine to. So if you are talking about breath rate analyzer, probably humidity or temperature, whatever you are monitoring at a very low speed and low amount of data, and the sensor itself could be a device, right? So these kind of applications you cannot think from silicon. So certainly there is a potential for these devices to be used in health monitoring and biomimetic application, biomedical application. And for all this work, I wish to acknowledge 3 students which graduated this year, who are Vivek Raghuvanshi, Ishan, Varun and Ajay Mato, and one more person who has graduated, I think, a bit back, like Deepak Bharti. So all these students who had done this wonderful work, which I could show to you, and obviously funding agencies and ministries and IT Jodhpur. So I had made it a bit short, and I hope to all of you it is kind of acceptable, and you can discuss with me if you are interested. Okay, so thank you. I think I would like to stop it here. Okay. So Dr. Mondal, is it fine, or you want something?
Yes, sir. Thank you, sir.
Yeah.
So from the participants, if have you any queries regarding this presentation, so you...
Hello, sir.
Yes.
Sir, if we use the organic transistors, it can biologically degradable. Then,
Yeah. See, organic transistors are degradable in oxygen. They are so many times. That's why these pentacene transistors don't work, right? But that is why materials like TIPS pentacene. Now, TIPS pentacene is a stable material. So you have to choose some materials which are actually stable. So most of the times, like gelatin. Now, gelatin is not degradable. Only thing, it just captures moisture, but it releases also. So that is where selection of materials is very important. And certainly, sometimes you want something, a product which is more like use and throw. It's like when you wear a gloves, you don't want to wear for 6 months, right? So there are products which have a lifetime, which is like mask. Now, if you wear a mask, probably you want to wear it for a month, right? Or if you have a e-patch or a patch on your body, now probably you want to wear it for say 48 hours or 5 days, or at least when you are ill and you want to be monitored by the doctor, right? So the applications for these biomedical applications for these organic devices will be more like for special uses. When you say health monitoring, so will be for special uses and not something which is directly coming into your mobile, which is there for 2 years. One thing is that. Second thing, obviously, degradation is there. And wherever you have invasive or direct in contact, there probably in some cases, if it is more like light sensing, then there is a way to encapsulate the device. But somewhere you want this device to interact, then you have to choose a material which doesn't degrade, or at least 5-6 months it is stable, right? So those things have to be thought of.
Okay, sir.
Yeah.
Sir, can we extrapolate these concepts to the area or to the realm of superconductors or supercapacitors, not conductors. Pardon.
Certainly. See, supercapacitors are one of the potential devices. See, whenever you say flexible, right? Now, when you say flexible system, which is smart, now smart, it means you want power also. Now, supercapacitor can be a very simple device which can be used for energy storage, right? So that can be a very useful device, and supercapacitors, and not only supercapacitors, like thermo electric nano generator, like TANG is a concept which just came maybe a few years ago. So they are like only just friction, if it bends, there is energy generation. So obviously this flexible electronics gives you huge scope of all these new thought processes which were anyway not possible with rigid silicon. So here supercapacitor can be very suitable, nano generators can be suitable, batteries can be printed, right? So yeah, it's a very good thought, and it is certainly in this kind of line.
Thank you very much, sir. Thank you.
Yeah, Mangnit.
And let's share the PPT so that we will refer it.
So any other questions?
Any other query?
If possible, kindly share the PPT.
No, I'll see. I think I can just re-put in a way. I'll certainly share. Probably I might need to remove something and leave most of the things. It's like I'll share with Dr. Mondal. But generally, it's like my talk is something, some certain things are still going on. So, you know, when you are in research line, you have to be always very, one is, say, if I'm presenting something from Rabe or Neil West, then I can easily, so that is some catch, but if you permit, I would like not to share, but if you request, I can certainly share the same thing. Fine, it's up to you. If you request, I'll share, else I generally don't want to share, but it's okay.
Okay, sir. Thank you, sir.
Okay, sir. Thank you very much for your valuable talk, sir.
Okay, Dr. Mandal.
Yes, sir.
Thank you so much.
Namaste, sir.
Namaste. Yeah. Okay, so I'll disconnect now.
Should you stay with us, sir, for a few minutes?
Okay. Yeah. I can be here for a couple of minutes, 5 minutes. Huh? Yeah, sure.
Over to you, ma'am.
Thank you, sir. And as we could have seen that within this 5-day course, we have learned a lot of things like topics on recent research work on microstrip antenna and frequency selective surface, importance of phase shift in the design of impedance matching, and many more, like importance of 5G network. And now I would like to request Dr. Kalyan Mondal, Assistant Professor ECE, NIT Manipur, and coordinator of this 5-day course, to give the vote of thanks.
Okay, thank you, ma'am. A very good afternoon once again to all the dignitaries present, experts, faculty members, and participants. I deem it a great honor and privilege to propose the vote of thanks on this day as we organize a 5-day from 17th to 21st January 2022 faculty development program on the trends of research and development of electronics and communication area. First and foremost, I, Dr. Kalyan Mondal, coordinator of faculty development program, on behalf of the organizing committee, thanks our respected director, Professor Gautam Sutradhar, NIT Manipur, who grace us with his guidance. My heartfelt thanks goes to the all experts of the FDP who will be enlightening us with their expert and experiences in this session to follow. I am also thankful to our main sponsors, AICT Training and Learning ATAL Academy, and to the entire participants as well as of this FDP. I am sure that our time and effort will not be wasted. Last but not the least, I take this occurrence to thank the entire organizing committee of this program for their effort and cooperation in making this program a resounding success. With this, I conclude my vote of thanks. Thank you all once again. Thank you very much. Thank you, sir.
Yeah, thank you. So I'll discuss. Best wishes.
No, sir.
Thank you, sir.
So dear participants, so we have to conduct a exam session, that is online MCQ type exam. So as pre-scheduled, we should start it 2 p.m. So please, and also we will share this link of the exam in chat box. So please, within 2 p.m, please join with us.
Sir, can you share the exam link on the WhatsApp group?
No, sir, it is not possible in WhatsApp group.
It's only a share in webinar.
Because of that, so many participants, they are not attending the FDP. All they are in WhatsApp group.
Okay. So this meeting is continue, or maybe this meeting is initiated.
Actually, meeting is finished. So if the participant want to attend the exam before time, so we are agree. But after 2 p.m. we can't consider it.
Sir, 2 p.m. is convenient times. Please make it 2 p.m. only. Okay, sir.
Okay. So
hello.
Yes.
Yeah, ma'am. Sir, meeting is continue, or maybe the meeting is reinitiate at 2 p.m.
2 p.m. Again we join for the exam purpose only. Okay.
Okay.
So before time, so please join with us.
Okay.
At 2 p.m. sharp 2 p.m. we will share the link.
Okay, sir. Thank you, sir. Thank you.
Okay. Thank you.
Sir, can I leave the meeting?
Sorry?
Leave the meeting. Can I leave the meeting?
Link?
Yeah, can I leave the meeting?
Yes, you can leave.
Okay. Thank you, sir.
Okay.
20 minutes is आयो इकरा दीदी के इकरा 20 minutes आयो तो दीदी इकरा इकरा इसे करूँगा क्या हेलो 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 ಮೂರ್ನೆಂಟು ಮೇಲೆ ಆಮೇಲೆ ದಾಸನ ಪಳ್ಳಿ ಅಳವಿ ಹೇಳಿದ ಹೋಗ್ಯದ ಕುಮಾರ್ ನಮ್ಮ ಇದು ಉಂದ್ಕೊಂಡು ಹೋಗ್ತಾರೆ ಹೋಗಿ ಬಂದತ್ತ ಬಂದ್ವಿ ಸರಿ ಅಲಿಕರಂ ನೈತೆ ನಿಮ್ಮ ಅವಸರಕ್ಕೆ ನಾನೇನ್ ಮಾಡದ ನಿಮ್ಮ ಅವಸರಕ್ಕೆ ನಾನೇನ್ ಮಾಡದ ನಮ್ಗೆ 4 ಗಂಟೆಗೆ ನಮ್ ಟೈಮ್ ಅದ 4 ಗಂಟೆ ಮತ್ತೆ ನಾನ್ ಮುಡಿಬೇಕು ಮುಡಿಯೋದು ಸುಮ್ಮನೆ ಹೋಗಮ್ಮ ಅಂತ ಒತ್ತಿ ಕೇಳ್ಗಿಡ ಇದ್ರದ ಯಾರ ಅರ್ಥ ದೇಶ ಸೋಮವಾರ ಹೋಗ್ತೀರ ಬಿಡು ಸರಿ ಹೇಳ್ಬಿಡು ನಾನು ಹೇಳಿಬಿಡು ಯಾನ್ ನೀನು ಹಿಂಗೆ ಅವಸರ ಪಟ್ರೆ ನಾನು ಒಂದು ಮುಡಿವೆ ನೈಟ್ ಏನ ನಾಳೆ ಇನ್ನೊಂದ್ ದಿನವೇ ಇರ್ತದೆ ಅದ್ರಲ್ಲಿ ಸುಮ್ಮನೆ ಅವಸರ ಪಟ್ರೆ ನಾವೇನ್ ಮಾಡಕ್ ಮುಡಿಯೋದು ಏನಾಯ್ತಂದ್ರು ಪೂರ್ಮಿಗ್ ಇರ್ಬೇಕು ನಾವ್ ನೆನ್ಸನ್ ಬಗ್ಗೆ ಮುಡಿಬೇಕ್ ಮುಡಿಯದ ಕಾಲೇಜ್ 5 ಗಂಟೆ ಮತ್ತೆ ನಮ್
Good afternoon once again. Good afternoon all. So now we are providing the link. So after getting the link, you may leave the meeting, no problem. Okay, after getting the link, you may leave. No problem. Deepak, am I audible?
Kalyan sir?
Yes.
Sir, is there any valedictory session which we have to rejoin later on?
No ma'am, no ma'am.
There is no validatory session, sir. And what about our certificates? Will it be uploaded on the ATAL website?
No. Certificate will come from the AICT direct.
Okay, so it will be reflected in our portal, or
Yes, portal.
And attendance also, right, sir?
Okay. I will provide all those information regarding our FDP and regarding our participants. I will provide to the AICT. Okay.
Okay, sir. Yeah.
After that, they will decide who will eligible for get the certificate.
Okay. Yeah. Thank you so much.
Okay. Deepak, am I audible?
Yes, sir. Sharing, sir. Sharing.
Okay. Share.
Sir, what time exact time duration for the exam, sir?
Actually, 1.5 hour.
So within 3:30 we have to submit.
Actually, it is depend upon the commencement of the exam start. Okay. So now to already to 2 p.m. like now, na?
Yeah.
So that means when we uploaded the link, from that you have to submit within 1.5 hour.
So 3:30 you have to submit maximum.
Okay. Almost.
Share.
Share exam link in chat box.
Yes. It is shared in chat box. Please see in chat box. It is given. So after getting it, you may leave as you wish. No problem. But you have to submit it within 1.5 hour.